Hey student, today we're getting started with Unit 3, which I've called More Derivative Rules. I'm still following the AP units. This would be including things like implicit differentiation and the chain rule. So today, our first lesson, we're going to get into the chain rule. So we've already learned the product rule, the quotient rule, the power rule, rules for exponential derivatives. But today we're going to learn about the chain rule, which is when we have a function within a function. So just with notation to start, we have f of g of x. So there's a function g inside of f of x. When we take that derivative, we have f prime of g of x. We take the derivative of the outside, we leave the inside alone, and then we multiply by the derivative of the inside. So just one thing at a time. I told you this with the product rule and with the quotient rule. We're only taking the derivative of one thing at a time. Okay, now we could have three or more functions inside of each other. So I'll quickly write the chain rule for three functions. We have f prime of g of h of x times g prime of h of x times h prime of x. We could do this with as many functions as we wanted. We have the derivative of the outside, leaving the inside alone, then the derivative of whatever's in the middle, so g in this case, and then finally the derivative of h, which was our innermost function. So let's try some problems. We have the derivative of sine of x squared. So you'll remember the derivative of sine is cosine. Cosine would be like our f of x. So f prime of sine is cosine, and we leave the inside alone. We leave x squared. Then we'll just multiply by the derivative of the inside, which is the derivative of x squared, or 2x. I would write this as 2x cosine x squared. Continuing on, we have 3 times tangent squared of x. You'll notice we had an x squared in the last one. In this one, we have a tangent squared. So sometimes it can be helpful for us to see this as the derivative of 3 tangent of x all squared. That squared on tangent is really on the outside of the whole expression. It's not on the x. So the derivative of that, we would bring down the 2, because our outside most function is, I like to say, something squared. It's tangent squared, but it's something squared. So we bring down the 2, be 3 times 2, tangent of x. And where we had a 2 would just now be a 1, so we don't need to write it. I'll write the 1, but we didn't need it. And then we'll multiply by the derivative of tangent, which we covered recently. It's secant squared of x. So combining all of this, we have 6 tangent x secant squared of x. Moving on, we have the derivative of 2e to the 6x cubed. You might remember the derivative of e to the x is just e to the x. So the outside function is e to the something. So e to the something that stays e to the something, 2e6 to the 6x cubed. And then we multiply by the derivative of the inside, 6x cubed. So that would be 6 times 3, x squared. Putting this all together, we have 2 times 6 times 3, 18 times 2 is 36, x squared, e to the 6x cubed. Okay, the next one, we are taking the derivative with respect to t, doesn't change anything, but we have 2 functions multiplied together as well as chain rule. So we have chain rule and product rule here. So we have sine of t and e to the sine of t. So what we were doing with product and quotient rule is picking one, picking a u, picking a v, writing them out, and then taking their derivative. So we have u could be sine of t, and v could be e to the sine of t. U prime would be cosine of t. V prime We leave e to the something alone, e to the sine t, and then we multiply by the derivative of the inside, which is cosine of t. And now we combine these, multiplying like so. So u prime v, v prime u. So u prime v would be cosine t e to the sine t. uv prime would be plus sine t e to the sine t times cosine t. Just getting that by doing the multiplication across. Okay, and then we can't really combine terms. We could factor cosine t e to the sine t out, cosine t e to the sine t, and that would leave a 1 plus sine t. That would be our derivative. And lastly, we have a bit of a challenge here. We have the derivative of ln of cosecant squared of 3x. So no longer an f of g of x, but more like an f of g of h of I of x. So we need to not get too excited or too nervous. We just say, okay, we have a whole inside. So ln of something, the derivative of ln of x, I'll remind you, is 1 over x, or 1 over something. We'll use that. Cosecant squared, yes, we've seen this before, it's familiar, but in terms of derivatives, it's still not one function. Cosecant squared would be like something squared. Could say u squared, and that would be 2u, and we're going to multiply by the derivative. And I'm getting a little bit inconsistent here with my notation, but we'll see our answer in a second. Then we would be taking the derivative of cosecant of something, I'll say u. The derivative of cosecant, we need 2 secants, 1 tangent, and it starts with c, so it's negative, so negative cosecant of u, cotangent of u, and we'll be multiplying by the derivative. And then finally, we would have 3x. 3x would just be 3. Okay, we can put this all together, and maybe I should have had ln of u to stay consistent here, times u prime. Okay, so putting this all together, the derivative of ln of something is 1 over something. So 1 over cosecant squared of 3x times the next function that we have, like the tangent problem before, was tangent squared. The squared was outside of tangent. So we're going to multiply by the derivative of something squared. 2 cosecant 3x. Then we're going to multiply by the derivative of cosecant 3x, cotangent 3x, and then by the derivative of 3x, which is just 3. Okay, so this is a big mess, but we have the 3 and the 2, which will become 6. There's only one negative sign, so it'll stay negative. We have a cosecant 3x and a cosecant 3x, so that'll be cosecant squared 3x and a cotangent 3x. And this is all over cosecant squared 3x. So we can actually cancel the cosecant squareds. So we would just be left with negative 6 cotangent 3x. And that actually simplified pretty nicely. All right, I hope the chain rule is making a little bit more sense, and we'll keep using it in the next videos. I'll see you there.